Welcome, dear children, to today's topic. Today, we are dealing with the last topic of the lesson, units and measurements, that is, dimensions and dimensional analysis. So, let me explain what is meant by dimensions. We'll start with some examples. Okay, so when I use the physical quantity distance, basically, what is this distance? We know about two types of quantities, fundamental quantities and derived quantities. So derived quantities are the quantities which can be expressed in terms of fundamental quantities. So what type of quantity is this distance? Distance, basically it is what? Length, which is a fundamental quantity. Distance is basically length, which is a fundamental quantity. So we can write, that is, if we write displacement, displacement also is a fundamental quantity. That means it is basically length. Okay. If I take area, what is area actually? In the case of a rectangle, when we consider area, it is length into breadth. Okay. So length is basically length. You know, what about breadth? Breadth also is basically what? Length. So length, that means area in terms of fundamental quantity, if I am writing, I will get length square. Suppose we consider volume. So what is volume? Suppose we consider the volume of a cube. Volume of a cube means what? Side length cube. Side length cube. So it is actually side cube. So basically in terms of fundamental quantity, what it will be? Length cube. Okay. So come to these things again. In distance or displacement, you have fundamental quantity length and its power is 1. And in area, you have the power 2 in length. And in volume, you have the power 3 in length. So, one more example we will consider, that is density. What is density? Density is equal to mass by volume. Okay. So basically that means mass is basically mass itself. Volume is basically what? Length cube. Isn't it? So when we write, it will be mass raised to 1. The power is 1. And length, what is the power raised to? -3. So we will say that the power of mass in density is 1 and the power of length in density is -3. This power of a fundamental quantity is called as dimensions. Okay, so the thing is this is what we mean by stating dimensions. What is the power of a fundamental quantity in a derived quantity? That power we call as dimensions. So here comes the definition of dimensions. The dimensions of a physical quantity are the powers or exponents to which the base quantities are raised to represent that quantity. Base quantities means the fundamental quantity. So in short, it means the powers of fundamental quantities. That's what we mean by dimensions of a physical quantity. So to represent dimensions of a physical quantity, we follow a standard method. In that method, we use certain letters to denote certain physical quantities. So we already discussed the SI system. In SI, there are 7 fundamental quantities. So to show that fundamental quantities, we have certain representations. That's what we are discussing now. So we have the 7 fundamental quantities here. Okay, and the dimensional expressions here. Let's discuss one by one. So mass has the dimensional expression m, capital letter M. So capital letter M within square bracket. So it is compulsory to write dimensional expression between the square bracket. Okay, double bracket it is. Now next is length. Length has L. So to represent length, the fundamental quantity length, we use the letter L. Then to represent time, we use the capital letter T. So don't get confused. T do not stand for temperature. T stands for time. So M for mass, L for length, and T for time. For temperature, we have the letter K. Capital letter K stands for temperature. And for electric current, the letter is capital letter A. That is the same as ampere. Here it is the same as Kelvin. Okay. Then for luminous intensity, we have CD. That small letter CD within square bracket. And last one, amount of substance, that is mole. Okay, so these are the dimensional expressions of various fundamental quantities which we have discussed. Now, in terms of these expressions, we will be representing the dimensional expressions of different derived quantities. That's what we are going to discuss next. Now, let's discuss the dimensional formulae of some quantities, how to obtain the dimensional formulae. First, let's start with area. Area, we know in most simple case it is length into breadth. So area, dimensions of area is equal to dimensions of length into dimensions of breadth. So dimensions of length it is L and dimensions of breadth it is, that also is L. So what is it? L square. Okay, so it's enough to write L square, but in mechanics it is common that almost all physical quantities will have mass, length and time. So in mechanics usually we write the dimensional expression in terms of M, L and T, the most fundamental quantities, the three quantities, mass, length and time. So in that way we can write like this also, M raised to 0, L square, T raised to 0. What does it mean? Area has got dimensions 0 in mass, 2 in length and 0 in time. So that is the meaning. So that way also we can do. Now second one, physical quantity is volume. So what is volume? Volume of a cube is side length cube. So dimensional expression of volume is equal to L cube, because side length cube, no, so length cube. So as I said earlier, it can be written as M raised to 0, L cube, T raised to 0. It means that volume has dimensions 0 in M, that means mass, 3 in length and 0 in time. Now the third one, that is density. Density is mass by volume. So dimensional expression of density is equal to dimensional expression of mass divided by dimensional expression of volume. So we have M, that is dimensional expression of mass is M, divided by that of volume is L cube. So we have M L raised to minus 3. So it can be written as M L raised to minus 3 T raised to 0, which means that density has got dimensions 1 in mass. So if no power is written there, means it is 1. So 1 in mass, minus 3 in length and 0 in time. Okay. Now fourth example, that is velocity. We know velocity is equal to displacement by time. Now what are the dimensions of velocity? Velocity, we can write length by time. Displacement has the dimensions length, time, t itself. So L by t it is. So L t raised to minus 1. So M raised to 0, L t raised to minus 1. So velocity has got dimensions 0 in mass, 1 in length and minus 1 in time. Now next physical quantity, speed. Speed, as you know, it is distance by time. So L by t, so L t raised to minus 1, M raised to 0, L t raised to minus 1. So we got the same for velocity also. So we can make a conclusion here, that is speed and velocity are dimensionally same. That word dimensionally is very important because only dimensionally speed and velocity are same. Otherwise they are, one is speed is what scalar quantity and velocity is vector quantity. So otherwise it is not correct. Dimensionally they are same. Now next physical quantity, that is acceleration. Acceleration is what? Change in velocity by time. Change in velocity has the same dimensional expression as that of velocity. So we have the dimensional expression of acceleration equal to Lt raised to minus 1 by t is equal to Lt raised to minus 2. So we can write it as m raised to 0 L t raised to minus 2, which means that acceleration has got dimension 0 in mass, 1 in length and minus 2 in time. Now coming to next, that is force. Force given by Newton's second law, that is mass into acceleration. So dimensional expression for force is equal to m. For mass it is m, acceleration Lt raised to minus 2. So it is m Lt raised to minus 2. Now, so it has the dimensional 1 in mass, 1 in length and minus 2 in time. Now next is work. Work is force into displacement. I think in 10th standard and 9th standard you have come across all these equations, force, work, energy, etc. Okay, so work is force into displacement. So work has got dimensional expression m L square t raised to minus 2. So 1 in mass, 2 in length and minus 2 in time. Now coming to next one, that is kinetic energy, half mv square. So dimensional expression of kinetic energy equal to, see here one point is to be noted, this half, a numerical constant, has no dimensions. Okay, numerical constants has no dimensions, but there are some constants like gravitational constant, etc., which has dimensions, but numerical values, they don't have any dimensions. So no need of writing any dimensions here. Then m, then v square, so Lt raised to minus 1 whole square. So ml square t raised to minus 2. So it has got, kinetic energy has got dimensions 1 in mass, 2 in length and minus 2 in time. So the thing is this, you should by heart the dimensional expressions of some derived quantities also, because we need it. This and all you can study, force, work, kinetic energy, speed, velocity, acceleration, such things you can by heart. So now the next one is potential energy. We know the expression for potential energy is mgh, where m is the mass, g is the acceleration due to gravity and h is the height. So taking dimensions of potential energy, we have m for mass, Lt raised to minus 2 for g, because what is g? Acceleration. Acceleration due to gravity, and h, L. So combining we have ml square t raised to minus 2. So this dimensional formula, the same dimensional formula we got for 3 physical quantities. You know which all ones? Work, kinetic energy, potential energy. So generally we say work and energy, they are dimensionally same. Work and energy, they are dimensionally same. That is a point to be noted. Now coming to the next physical quantity, that is pressure. Pressure is equal to force by area. Okay. So finding the dimensional expression, we have mlt raised to minus 2 by L square, that is ml raised to minus 1 t raised to minus 2. So pressure has got dimension 0 in mass, minus 1 in length and minus 2 in time. So only this many derived quantities we are doing. Now we will discuss dimensional formula of a constant, universal constant, that is gravitational constant G. So what are the dimensions of gravitational constant? So how will we get? From the equation which we studied in 9th standard. from Newton's law of gravitation, we wrote this equation. What is this equation? The force between two masses m1 and m2 separated by a distance d. That force is given by g m1 m2 by d square. Okay, so rearranging that equation, we will have G is equal to Fd square by m1 m2. Therefore, G is equal to ml t raised to minus 2 into L square. Okay, this is of force and this is of that distance square. Then m1 into m2 no here. So, m into m. So, it becomes m by m square. So, m raised to minus 1 L cube t raised to minus 2. So, G has got dimension minus 1 in mass, 3 in length and minus 2 in time. So, G has got dimension. So, G is a dimensional constant. There are some constants which are dimensionless. We will discuss some of them. Now, we have some dimensionless quantities. First one example, it is refractive index. You know what is the expression for refractive index? It is C by V, where C is the speed of light in air and V is the speed of light in any medium. So both the C and V, they are speed or velocity. So both have the same dimensional expression. So we have no dimensional expression for what? Refractive index. So refractive index is a dimensionless quantity. Now coming to relative density. What is relative density? Density of a substance by density of water. Density of a substance and density of water, they have the same dimensional formula. So we have relative density without any dimension. Then third one is plane angle, that is arc length by radius. Arc length and radius both are what? Length itself. So L and L. So no dimension. So plane angle is a dimensionless quantity. Solid angle, area by r square. So area has got dimension 2 in length. R square also 2 in length. So no dimensional expression for solid angle also. So these two are the two special quantities, not considered as fundamental quantities. They are specially, they belong to a special group called supplementary quantities. This is the reason why they belong to that supplementary group, because they are dimensionless quantities, but they are to be measured. It has got some unit. Radian is the SI unit of plane angle and solid angle has got unit steradian. So that's why these two quantities are called as supplementary ones. Okay, a special group, because they are dimensionless one. So only this much for today. Thank you.